Well, welcome back, everyone. So we're heading now into the last two sessions of our conference. For those of you who I haven't met, I'm Di Allen and I'm one of the directors of Unimutual, and I'll be guiding you through the last part of our conference. Our next speaker, Dr. David Henderson, is the Research Director at the Cyclone Testing Station at James Cook University, and I'm thinking about Cyclone Narelle, which has managed to go from one side of the country to the other, so I think we're very lucky to take him away from his studies and observations at the moment. So with more than 30 years experience investigating damage from extreme wind and hail events, David has worked extensively on testing building materials and informing our national building standards. So today he's going to share his insights from the joint project with Unimutual with TEFMA, where the Cyclone Testing Station has conducted full impact testing on materials commonly used across our sector's buildings. And you'll see how the testing is performed, and including the ice ball cannon, and we all love a bit of explosive activity around a university, and you'll hear the early findings that will guide our resilience planning. So could you please welcome Dr. David Henderson.
Thank you. All right, good morning all. Thanks very much for having me here. To no relation Jeff and to Simon for getting me down here. In terms of what we're going to talk about, it's a bit broader than that. It's going to talk about really why our buildings are failing us in terms of many aspects. It could be wind, rain, and hail. So we're going to cover a fair bit of aspects to it. We're going to go through a bit of the station, just very briefly, and then start talking about our codes and standards. And we're going to take examples from different events, cyclones and hailstorms, to come to the conclusions. Just very briefly, the Cyclone Testing Station was formed in 1977 after the devastations caused by Cyclone Althea and Cyclone Tracy. We do everything from testing roofing screws to breaking complete houses. I've been at the station since 1991, which basically shows I have no imagination, or it could be it's the best job ever, one or the other. We do have different things. We have wind tunnels. We have a lot of aspects in how to understand the aspects of what makes a house work or a building work or not. But our main learnings really come from seeing what happens after an event goes past. So storm, hailstorm, cyclone, it is the ultimate learning. And yeah, I will be on a plane tomorrow to go over to Western Australia. From a lot of that, we bring things together to look at how we can better shape our codes and standards and the tortuous process that is, as well as informing vulnerability models and helping the insurance industry and government regulations. So really briefly, Cyclone Tracy, it was a major event in terms of how our codes and standards responded and also to the devastation it did to housing. So about 90% of housing in path of the cyclone was destroyed. They were winds in the order of about 240 kilometres per hour, a low-end Category 4 cyclone. Currently we've got a Category 4 going through Exmouth at the moment, about 200 kilometres per hour winds. That made some massive changes to it, and a lot of it came about that a lot of our building codes and standards around extreme events was around act of God. So if something came and blown down, it was all, okay, there we go, we'll put it back up again. It was around a traditional form of construction about building stuff up, not tying it down into the ground. Cyclone Tracy made a huge impact, and well, we've got to do better. Because for a cyclone or a lot of storms, we get told to go home. So our houses have to be a place to shelter. So a lot of engineering has to go into that, plus all our other buildings as well. So in many ways, our codes and standards are, not in many ways actually, our codes and standards are reactive. I try and be more positive, but they're really a reactive type thing. So we go along for a while, then something bad happens, like say Cyclone Tracy. There's a big jump up in terms of what that means in terms of our performance criteria. The codes and standards are really focused on life safety. And we'll talk more about that, what it means in terms of how our buildings work for us. But in terms of code and standards, it's life safety. Then as time goes on, that performance criteria might be up and down depending on things that might get learnt. But within the National Construction Code, especially in terms of structural provisions, it's basically about making sure the building stays intact, protects the people inside, not the contents. The code is around protecting the people inside. And it's also about making sure some of your building doesn't go and hit somebody else's. That's basically it within terms of the structural provisions. Within the National Construction Code, since it's legislated by all states and territories, the primary reference is our loading standards. So in this case, I'm talking about the wind loading standard, it's 1170.2. And with that, it divides the country up into different regions, wind speeds. So I'm from Townsville, up north, so I'm in a wind region C, which is about 70 metres per second measured at 10 metres height and flat open terrain. That's the benchmark, the world standard for measuring wind speeds or referring to wind speed. So flat open terrain, 10 metres height. Within the NCC, it sets the societal risk that we all agree to within our building codes and all the states and territories sign on to. So for general buildings, importance level 2 buildings, it's this 17 metres per second is our design criteria. If you're over in Western Australian Region D, currently where Narelle is going through the bumpy bit there, your design wind speed is 300 kilometres per hour for that importance level 2. If we're down here in Region A, we're down about 160 kilometres per hour in this area for that design level. We're thinking, well, that's pretty good. That's the minimum criteria we've designed to. So it's like saying we've got latch-sash seatbelts for our cars. We don't have airbags, we don't have crumple zones, everything else. So when they get the builder that comes along and say, built to the standard, you go, congratulations, you made the bare minimum. Because that's what the criteria is all around with it. And it does come back to bite us in many ways. But we'll get to that. Firstly, in terms of wind loads, as the wind's coming into the building, hitting the wall, going up over the roof, it's putting a lot of positive pressure on the windward wall, trying to pick the whole building up by its roof. The roofing's connected to the purlins, the battens are connected to the trusses, the rafters, the wall, wrist bone connected to elbow bone all the way down to ground level. That's basically how the structure works. If on the windward wall, the window breaks or a door blows in, that windward pressure instantaneously enters into the building space, doubling the load on the structure. Now in cyclone regions C and D, again where I'm from, we have to. Most of the times we're designing for that. A lot of potentially corporate buildings, commercial buildings, say they don't have to design for it because they'll talk about having an envelope that doesn't have a potential opening. So they might talk about screens, they might talk about toughened glass or aspects like that. But generally we should be designing that for cyclonic regions. For regions down here, it's very rare, unfortunately it's quite rare for design for full internal pressure, for all types of buildings, housing as well as our commercial properties. This is a video from IBHS, the lab over in the US. It's an insurance-funded research lab. It's a very, very cool place to visit. Been there a few times. They have a wind tunnel that you can fit 2 houses in. Now, if you notice the house on the watch-hand side, the left side, it's actually missing a window before they start the test. So it already has the internal pressure working against it. The one on the right is called their fortified house and it's strapped down. It's like one of our cyclone houses. It's got a lot of steel tying that timber frame down. But regardless of that, you can see the impact of internal pressure doubling the load across that roof structure and the roof disappears. So already in our National Construction Code, we really have 2 levels of risk. We've got the people in the north that are designing for internal pressure and the rest of yous that aren't. So even though we talk about the same societal risk level based on the recurrence interval of these wind speeds, you're already at a disadvantage down here if you go away, you talk about your house, 2-story house, shower in the morning, you leave the bathroom window open, you head off to go to work, storm comes through, pressurizes the top story through that bathroom window, your roof disappears. We've done investigations in New South Wales where that has happened. So again, these issues are real. But let's talk more about it when we talk about Cyclone Seroja. This is, it was a very scary event a couple of years ago. going through Western Australia, not dissimilar to what Narelle's doing. Narelle's closer to the coast at the moment. At the moment. The cyclone was a Category 3 going through Kalbarri. One of the reasons many reasons we do damage investigations is that it's one of the main drivers that we get to influence codes and standards, because they always show us the examples, as opposed to research and other things like that. But around that, we get to see, are our design standards appropriate? Was the wind speed exceeded? Was it more than this minimum level? Was it was it built correctly, designed correctly? Was it the right materials? Were they conforming materials? Were they dodgy imports, whatever it might be? And were they being maintained? Which is a big crucial one now, because our codes and standards came in those 80s and 90s. Some of our houses are more than middle age, or other buildings, so like me, very thin on top now, so it needs a lot more maintenance to keep it going. So one of the jobs we do when we go out, we look at the wind speed. So this is a contour map of percentages of our design wind speed. So you can see from that, Kalbarri almost got to its design wind speed, being in wind region B. It was just outside the cyclone region. The cyclone region ended just north of Kalbarri. So wind region B, but less than that 180 km/h wind speeds for its design. So again, sweet, great. Yes, there was damage to older construction. You can see some of that on the screen. So some of the older construction lost roofs and things like that. But when we started doing the damage survey, working with emergency services over there was over 30% of modern construction had significant structural damage. So this is one of the biggest percentages of wind damage we'd seen since Cyclone Tracy go through, which again was in a huge different kettle of fish. What it really was is that because of the event was generating debris, parts of houses coming off branches, breaking windows or doors blowing in, so doors aren't wind rated in these regions, they pressurise those houses. Those houses then lose roofs and other parts, they go through the next house. That loses stuff. So it's a big avalanche or a snowball, growing snowball of damage as it moves across the region. And you can see in that photo there's complete roofs have come off and hit things in terms of the wind speeds going through. Debris is travelling 400, 500, 600 metres in these wind events, leading to huge amounts of damage across the town there. And it's not just housing, it was commercial structures as well that were impacted by this. So there have been proposed changes to the wind loading standard based on this damage, but for wind region B2 only, it's a transition zone from cyclone region. It's a small borderline. It doesn't impact the wind region B where Brisbane and southeast Queensland is. In terms of wind-driven debris, there is an Australian standard test for it. It's a chunk of timber, but it's meant to represent so many other things. Could be a 4 kilogram roof tile, which really do travel very well, or could be up to a whole half of a shed that wasn't built correctly. It's all representative around this test in the standard. Yes, it is a fun test to do. And we get to do lots of different things with it. But what it does show that pretty much anything will go through something. We did get carried away. I haven't got the pineapple on here, but that pineapple took the whole door off. Mess to clean up, but it did the road. So one of the things we really try to advocate is great protection for our windows and for our doors and stuff. So this is an old picture, but I really like it. It's got a really nice, cheap, simple debris screen. Might look a bit ugly, but it's built off from the window. When it gets hit by something, it's got time to absorb that energy as well, and that doesn't break the window behind it. Unfortunately, the door blew in, pressurized the building, and the roof and the wall went out. So when we talk about protecting the envelope, we mean we've got to protect all the envelope. So down here, and in Brisbane, southeast Queensland, places like that, there are no wind-rated doors. You don't have to have wind-rated doors. So your normal entrance doors and your normal lock sets will easily burst through the timber striker plate. Your large garage roller doors, then you can get wind-rated doors. Most people don't think to ask, and it doesn't have to be there within the codes and standards, so you don't have to get it through there as well. But that is a major risk factor in our modern buildings. So back to our wind load map for the country. So we've been over in Western Australia. That same latitude is over where southeast Queensland is. And so Cyclone Alfred comes along. Now, this was really, really scary for us. We'd done some vulnerability modelling for the Queensland government about a year beforehand with Geoscience Australia, and we were looking at projections that if a Category 3 went through southeast Queensland, through that Brisbane Gold Coast area, we were looking at about 120,000 houses that would be structurally damaged to the extent you couldn't live in them. And that's just structure. That's not other aspects to it. That's not power, not anything else. So it was a really great relief that this thing died before it got to the coast, because it was forecast to come in as about 150 kilometre-hour winds. So when we did the wind mapping, yes, the wind speeds were well less than the design wind speed for the area, only about 100 kilometres per hour. So many things were saved in that regard. That's not fast enough to take roof tiles off our roof. That's about 120 kilometres per hour. Trampolines start flying around, just before that as well, if you don't tie them down. Wheelie bins and branches and stuff, about 100 kilometre an hour, really just fall at the base of the tree. Decent branches to break windows and things. So this was just below the threshold before bad stuff happens. So incredibly lucky for this part of the country with that event coming through, because if it had come through at that wind speed, we would still be cleaning up from it. It did highlight, however, just dumb stuff. So poor maintenance. It wasn't just in housing. There was commercial properties that hadn't been doing maintenance, and that highlighted that. The 14-storey building there, the face brick, so the brick ties that you can see in the middle of the screen, they were completely corroded. Not like they were next to a surf zone in the Gold Coast, of course, but completely corroded through that. Even very early on in the wind speed, this had actually come off and ended up in the car park below. Thankfully, nobody was underneath it when all that brickwork came down. So that was one of the bigger examples of it, but we saw this repeated throughout the region in terms of just poor thought in terms of the durability of materials and how hard it is to try to maintain or replace some of these things. We did see damage to modern commercial construction, especially at podium levels. In terms of medium or high-rise buildings, a lot of the wind hits that wall, gets pushed down to street level, slamming into other buildings and blowing doors inwards and things like that. There was a heap of wind-driven rain, other aspects of flooding and all those things going on with it. In terms of the wind-driven rain, the duration of this event was, some of you would have been there for it, so in terms of 36, 40 hours of wind-driven rain coming against. Now, all our codes and standards, when we talk about rain, talk about the rain just falling out of the sky. In any wind event, the rain's doing this. But our codes and standards aren't designed for this. The codes and standards believe in gravity, and they just think everything works with gravity. The wind doesn't believe in gravity, and it will push the rain back up our roofs. It'll push it up our valley gutters, under the ridge capping, dropping into roof spaces. It will coat our walls enough. So if you've got a masonry wall, unpainted brick wall, unpainted masonry, concrete wall that has not been surface treated properly, it just loves the water and sucks it in and draws it through. The hotel that we were staying in, there was so much water coming through the windward wall, we were paddling around in the carpet. Still had power on and was still charging stuff, so that was fine, I guess. But yeah, a lot of water coming in through all these areas. And then it was getting down into basements, flooding basements, taking out the generators, taking out the switchboards. Buildings were losing power. People with electric cars were quickly trying to get them out of the water, because imagine what that would have done. And the other thing from it, so in one way, it was really good the wind speeds were so low, because we got to learn about a lot of the dumb stuff that gets masked by higher wind speeds. In terms of some of that dumb stuff is that with a lot of this water coming through, either through the roof spaces or through poor flashings or poor wall treatments or glazing aspects and everything else, it was getting in behind our switchboards, our circuit breakers. It was getting into our fire panels. So there was a 170% increase in call-outs to the fire services through southeast Queensland during this event. It was getting to the stage they were just sending a car with an officer in just to see what was going on, because there was a lot of false call-outs. Unfortunately, the percentage of fires did also increase due to circuit shorts, things like that with there, and also people barbecuing inside their apartments. It's a stressful environment. It's also taking out our backup power, which is our sump pumps and funding. It's also taking out the power for our lifts. So all those things aren't working. Refrigeration, all those aspects. People weren't testing their generators under load. So there was people going, great, we've got a massive generator for our facility. Let's go it just blew up because everything was turned on and everything else. So again, they lose what they thought they had as their backup power system to it. So operating procedures really need to get changed to make sure that what we think we've got as a backup actually can be a backup. And also testing that if you've got an agreement with a person that's a company that's going to bring a generator, they've actually got enough to go around. So having that backup may not be a good solution if you can do a design brief better so we don't get the water in the first place. Because remember, the codes and standards ain't doing that. We've got to do that ourselves. We've got to talk to the designers. We've got to talk to the architects. We've got to do better to keep the water out in the first place. Because codes and standards are a bare minimum. They're not about resilience in terms of the structural provisions. They're about life safety. They're not about functionality. So our codes and standards ain't helping us protect what's important to us inside apart from the people. So we need to do better. We need to think about how to improve our buildings. We get so much wind-driven rain coming in because the current test methods and test standard is so low. It's about 1/10 of the serviceability requirement, which means operational during winds. But even that wind-driven rain component is so low on the pressure, water comes in normal storms. It's just within larger long-term events, it's making so much more water coming in. So a couple of days, a couple of weeks after an event goes through, the ceilings start collapsing because all the water's come into your roof space or come into the floor above or all those things with it, dropping out ceilings, mold and everything else with it. This is from Cyclone Debbie. It's from one of the apartment buildings there. That rain is coming through a Australian rated standard door. It's even coming through the fixed end. The ceiling system's not quite right on it. Coming across the Parkbury floor, not a big deal. Insurance to get that one for us. As the camera tilts up, you can see the water coming through the ceiling above, which is the floor of the bathroom above, coming out through the light fitting, raining down. Some of it's ending up in the bathtubs, that's all right. And when the camera pans around, see people in front of the windows, and the TV's still on. So there's still power on, you're walking around in it. I can't comment because I do the same. It's environment. However, of all the thunderstorms, cyclone stuff that we do, for commercial engineered properties, we see over 70% has some form of water ingress. Some of it is because maybe a tree's hit it. A lot of it is to do with wind-driven rain coming through. So all of this stuff is not really covered in our codes and standards of design as I keep harping on about. So it's something we need to be really cognizant on and do a lot better because it is driving a lot of our insurance premiums. It's driving a lot of disconnect within the communities afterwards. Our houses have protected us, our buildings protected us, but we can't go to the kindergarten, we can't go to the shops, we can't do it because their ceilings have collapsed with it. So it is a major impact on our communities. Another thing we're talking about, resilience of PV systems. So take this example from Cyclone Ilsa a couple of years back. It had, just go back. It was a category 5 system, so incredibly severe event coming through a relatively unpopulated part of Western Australia. That panels, those ground mounted systems you see there, we're right on the coast, subjected to those really, really high wind speeds, 280 kilometers an hour, I think, at that point with it. So we can build stuff to resist those wind speeds. Things do exist to do that. Those panels there show we can do it, we can get it right. So in terms of the damage surveys, we went through, tracked the cyclone as it went through all the different wind regions. It went a long way inland, so it went through a region D, C, B, and A to really non-cyclonic regions when it was starting to degrade a lot, and looking at the percentages of wind speeds. All the way up through, it didn't exceed the zone anywhere it went. But apart from that example on the coast, there was nothing but grief to the panels all through there. To the extent that some of the small communities were solely reliant on their solar panels now, like in that shipping container, was the battery storage. They kind of decommissioned their diesel generator for their comms and refrigeration and everything else, but the panels went during the buildings. So we've got so much damage happening to our solar. When you dig a bit further into it, although we've got a Australian standard for solar, which is really around electrical regulation, and it does talk a little bit about wind loads, there is no building regulation with the NCC about what design level you make that attachment to your house. When we talk to the different states and territories, they talk about it, well, it's kind of the same as an antenna, isn't it? Except these are 20 kilograms and they fly a long way, and they can take part of your roof with it. Because it's like a biplane, you put another wing on top, so you've got additional wind load as well if you put it, depends on where you put the thing. So we get a lot of these installations actually doing more harm on their building because they're there, and if they're not installed correctly, they can then leave and hit other people's buildings as well. Starting to get the theme here in the codes. Hail. So yes, it's a massive point in terms of the dollars cost to the communities with coming with it. From all the modelling of the climate change aspects to it, hail is going to get more severe in terms of size, in terms of frequency in certain parts of the country, especially on the east coast with it. As mentioned, we've got a project with Unimutual and TEFMA to start looking at some of these aspects to it. So investigating the performance of metal cladding, roof tiles, plastic sheeting, and PV panels to start with. Coupling that with the data from Unimutual to look at how we can better inform codes and standards to say, hey, look, this is a real issue. We need to start doing more around it. And also talk to product manufacturers about what we're going to publish with that. Go talk to them with it. So yes, we get to make, in the tropics, we get to make ice balls and we get to throw ice at certain products. You'll see what the impact where that ice ball hits. This is to the Australian, it's not Australian, there is no Australian test for hail. What it is that they reference it for some products, not metal roofing, that you can use the American test or there's a European test for different types of hail. This is the American test. It's got a 35 or a 60 millimeter ice ball. That's a 60 millimeter ice ball thrown at some unsuspecting building product. If you look at the impact location, you can see a very tiny dent that it's made on that rib. A previous location was in the pan of that. Because there's a tiny dent there, most roofs get replaced because of whatever the reason is in terms of the PDS on visual appearance, things like that. Australian roofing manufacturer or supplier BlueScope on their webpage says that very small dents from hail, impacts from hail do not affect the warranty of the product. Their coatings and everything else can take abrasives, can take this. If the roof slope is enough so that dent that it makes, it doesn't pond moisture, so there's less chance of corrosion, that's fine. However, they do say that if there's a small dent near the lap where the two roofing sheets meet, that may affect the capillary action, which means as water's running down the pan, it can, if those two laps meet, it can draw water into the roof space. They give no number or line in the sand on what a small dent is. So they don't say what a pass or fail is with it. So the net result of that is that there is a lot of roofing that gets replaced during these events, probably when it didn't have to. The downside, apart from the cost and the wastage of material, is that you've probably now got a weaker roof because they've just taken those whole roofs off, putting them back, re-screwing into the same battens or purlins there, weakening that system. So in the next wind event that comes along, you may actually have a weaker product because you've asked for that new roof to go on with those small dents as an aspect to it. So hopefully we'll be able to get some quantitative information with this project to really go back to the industry with. Obviously hail is a big impact on solar. There is an Australian standards on solar more around the electrical of it, regulation of it, but it does talk about wind and weather. It does not mention hail in there. However, it does have a reference to the international standard, IS something or other, 621 in there, which does have a 25 millimetre hail test. Most solar panels imported into Australia do pass that test, but that's only 25 millimetres. There is criteria for a bigger hail to it, but not many do for that one. So there is stuff out there that exists, but what it doesn't talk about is what micro-cracking and other aspects could be there in terms of moisture getting through and the loss of the function of that solar panel with it. Interesting quote from the ABC from Adam from Standards Australia. Adam's a great bloke, runs a lot of these codes and standards that we station sits on. The interesting thing was he talks about this criteria, this international criteria, and that it can be applied. But the one that really took it is that standard revisions generally run between 3 to 5 years at the international level and are based on data. That's true. However, in Australia, our code cycles and the time it takes to get through, it's more like 10 to 20 years. So the stuff that we learn now, unless it's, say, a fire issue in terms of, say, a backpacker burns down or something that's really direct related that can make it, in terms of a lot of our wind loads, earthquake loads, all those types of things, it's a decadal cycle to get into a change. So again, if we're looking at our design of our structures, we can't really look at what our codes and standards are doing for us in that regard. So to summarise, climate change, we're all aware is happening, and it's happening at a faster rate than what we're really thinking about in terms of our building environment. Our codes and standards are not keeping up with that. Well, they don't keep up with it now. They're not keeping up with what's coming as well. So we can't keep waiting to react at these events and then put something in practice 10 years later. It's just not working. So we need to be thinking about how our buildings and products are evolving and be in front of that without the code cycle. So when you're looking at your buildings in 25, 50 years' time, are you going to be building the same thing you're doing now, which is going backwards, or are you going to adapt and build better, build beyond the minimum? Thank you.